Hello and welcome back. In this video we'll start Chapter 5, Section 1, which is going to be about probability distributions and some specific discrete probability distributions. And I'll talk about what discrete means in a second. But first, let's again look at a couple of vocab terms. So a random variable is going to be a variable that takes numerical values, and each value is going to be just a single value. It's determined by chance, and we'll determine that for each outcome of a procedure. So before I go any further, an example of a random variable might be the number of heads that you get out of 4 coin flips. So you could get 0 heads, 1 heads, 2 heads, 3 heads, or 4 heads. So the number of heads is a numerical value, and you only get one number of heads, as in you can't get both 1 heads and 3 heads at the same time. It's only one value, and it is in fact a value as in a number. Now, along with a random variable, we can talk about a probability distribution. And essentially, this just says what is the probability for each outcome of the variable. So when we're flipping a coin, say 4 times, there will be a 1 in 16 chance that we'll get 0 heads, which is 0.0625, so about 6% of the time you'll get 0 heads. Whereas 2 heads is most likely out of 4 flips, and that's at 37.5%. Which is more than any other particular one. So some more examples here. So for instance, the time it takes to solve, say, a math problem. This is a random variable because the time it takes to solve a problem is, again, a number. So it's a numerical value. When you solve a problem, you only get the time it takes to solve a problem, there's only one time. So this is going to be a random variable. The number of attempts before making a free throw in basketball, again, if you're counting something, this will be a random variable. And then this last one, the number of hearts in a hand of 5 cards. So if you're dealt 5 cards from a deck, the number of hearts you have, again, it's a number. So this is going to be a random variable. But if you're conducting a poll and you're asking people what is their favorite sports team, this is not a random variable, because your favorite sports team isn't going to be a number. It's not counting anything. It's just going to be a name. And likewise, whether a coin lands heads or tails, this is quite a common probabilistic thing to consider. But the values heads and tails, those aren't numbers. So if you are just asking whether a coin lands heads or tails, that's not going to be a random variable in the sense that this isn't going to be a numerical value. Okay. And I mentioned that this chapter is mostly going to focus on discrete random variables. So the word discrete here means that there's going to be separation between the possible outcomes of a procedure. So a more technical definition would mean that there are either finitely many or countably many possible outcomes, as opposed to a continuous random variable where there are infinitely many possible outcomes and you can't count them. So let's go through a few examples. So if we come back up to these guys, so the number of hearts in a hand of 5 cards, is this discrete or is this continuous? Well, the number of hearts that we could get would either be 0, 1, 2, 3, 4, or 5. That's a finite list of outcomes. Therefore, this is discrete. Again, because there's a very specific set of possible outcomes, and it's a finite list, this will be discrete. The number of attempts before making a free throw, this is also discrete, even though there are infinitely many possible values here. If I were going to go shoot a free throw, I might make the free throw on the first try, on the second try, on the third try, on the fourth try, And this list could go on forever. It could be up to millions of times, billions of times. So there are infinitely many values that this can take. But if we stop to think about it, each one of these values is sort of separate, and I can talk about the next one. There's always a 1, a 2, a 3, a 4. There's nothing in between, and this is going to be discrete. The way that mathematicians will describe these values is that they are countable. The number of outcomes here, I can count them. 1, 2, 3, 4, 5, 6, and so on. The time it takes to solve a problem, this is going to be continuous. And there are a couple of different ways to see this. The first way is to think about, okay, if we have a timeline about when we're going to solve this question. Over here we might have, say, 0 seconds. And then over here maybe we have 100 seconds. But we can see that between any two values, between any two times, I can find another time. So it doesn't matter. It can take however long we want, even in between any two times that we could possibly have. There is a continuum of possible times. Okay. Another way to see this is that there are infinitely many times it could take to solve a problem. More than 100 seconds, less than 100 seconds. Any fraction or decimal that you could ever want, and we can't count them. There's no possible way to count all of the fractions, all the decimals between 0 and 100. So since we can't count these, this will be continuous. We are going to focus on discrete probabilities in this chapter. So ones where there's either a finite list of possible outcomes, or there's an infinite list, but it's somehow nice because I can count them. I can write a list of all of the possible outcomes. Some things to note about probability distributions. Again, this is only for numerical data. We're not really concerned with categorical data at the moment. The probability that something happens is going to be 1. And when you add up all the probabilities of all the different events, the sum should be equal to 1. Because we know something happens, there must be an outcome. So the sum of each of the probabilities should be 1. And then likewise, the probability for any one event should be between 0 and 1. If it's exactly 0, the event can't happen. If it's exactly 1, the probability of the event is certain. If it's somewhere in between, there's a chance it might happen and a chance it might not. Now, there's a small caveat here. Sometimes the probability is so small it rounds to 0, as in it might be 0.00000001. And if we're rounding to the first decimal place, we're rounding to 0. However, if it is positive, if it's still strictly between 0 and 1, but it rounds to 0, we will write that using 0 plus, meaning it is possible, but very, very unlikely. As in really, really close to 0, but not quite 0. So this is just our notation for that. The last thing that we'll look at in this video are some parameters here. So again, we'll use x to denote the value of the procedure. We could use any letter we want here, but quite often it'll be x. P of x is just the probability that x happens, the probability that x occurs. And then there are the two parameters that we've seen before. We have the mean and the standard deviation. Mean, because we're looking at an entire probability distribution, we're looking at the entire population. So we're going to use mu rather than x bar to denote the mean. And the standard deviation, which roughly tells us how spread out the data is, or I should say the data are. We'll use sigma because this is again a population. We're talking about the entire population, not just a particular sample. Remembering that the standard deviation squared is called the variance, and most of the time the standard deviation is going to be more useful to calculate and to know. So the formulas for these guys, the mean is going to be the sum of each of the data values times their probability. And this is, there's nothing more to it. We just take each value times the probability that it happens, and we add it all up. The variance, or in fact to calculate the standard deviation, I would just take the square root of this. But for the variance, for the moment, again, we want to look at the difference between each data value and the mean to see how far away it is. We'll square it and take it times the probability. This, in general, is how computers will calculate this. For us, by hand, this is in fact going to be a little bit easier. These are the same formula. You can get one from the other. But the second one is going to be easier to calculate by hand. And in order to calculate the standard deviation, I just take the square root of the variance. So let's see these guys in action, and we'll show you how this all works. Forgot my parentheses there. So if we come back to the number of heads out of 4 flips, I could get 0, 1, 2, 3, or 4 heads. And their probabilities I've written as fractions. It's a little bit easier to multiply these guys rather than using decimals. So let's calculate the mean, and we'll see if this makes sense. So the mean is, again, the sum of each of the values times the probability that it happens. So let's multiply these together and add them up. So we will have x times the probability that x occurs. So x here is 0 times 1/16. Well, that's 0. 1 times 4/16. Anything times 1 is just itself. 2 times 6/16. That'll be 12/16. 3 times 4/16. Again, that will be 12/16. And 4 times 1/16 is 4/16. And now the sum of each of these guys, we just have to add each one of these up. So this will be 4/16 plus 12/16 plus 12/16 plus 4/16. And this is relatively easy. These two add up to 16/16, and these two add up to 16/16. And when you add, so 16 divided by 16 is 1, 16 divided by 16 is 1, so the mean is 2. And this makes sense. If we're going to flip a coin 4 times and count how many heads we're going to get, you would expect, sort of on average, that you get 2 heads. So this makes sense for a mean for this. Now let's compute the standard deviation. What I'll do is I'll calculate the variance first and then take the square root. So this formula is nearly the same, except that instead of looking at x times p of x, what we want is x squared times p of x. So x times x is, so for this first one, 0 times 0 is 0, times anything is still 0. 1 times 1 is 1 times 4/16. 2 times 2 is 4. 4 times 6 is 24/16. 3 times 3 is 9. 9 times 4 is 36. And 4 times 4 is 16. Times 1 is 16/16. So this formula, we add these together and subtract the mean squared. So we're going to add each one of these up. So we will have 0 plus 4/16 plus 24/16 plus 36/16 plus 16/16, and then we're going to subtract the mean squared. The nice thing is that all of these guys add up to exactly 80 over 16, and 2 squared is 4. 80 divided by 16 is 5, so this whole thing is 1. So the standard deviation is the square root of 1, which is 1.